Hey everyone! If you've ever wondered why your FEA results just don't seem to match up with those real-world shaker test failures, well, this explainer is definitely for you. That's right, today we are going to pull back the curtain on random vibration. We're going to take the randomness out of the equation and give you a super practical guide to nailing this in a Bacchus.
All right, so here's our game plan. We're going to start with the basic concept, then get into the key lingo you'll need. We'll talk about why this is so important and build up the intuition for what the solver's actually doing. After that, it's all practical stuff, the abacus workflow, and then the big one, how to read the results and, more importantly, what mistakes to avoid. Okay, let's get right into it. So I think most of us coming up have done a standard frequency analysis, a harmonic analysis. What's the real difference when we add this word random in front of it? What changes? That is the perfect question to start with. And this slide really nails the difference. So over on the left, you've got your textbook deterministic vibration. It's a perfect sine wave, it's clean, you can predict its exact value at any single point in time. But the real world is messy, right? It's more like what you see on the right. Just think about a car driving down a bumpy road. That motion is a chaotic jumble of different frequencies. It's totally unpredictable from one moment to the next, which means we have to switch gears and start thinking about it statistically. And this image right here just drives that point home. I mean, look at this waveform. Could you tell me its exact amplitude, say 1 second from now? No way, it's impossible. And because it's so inefficient to even try to analyze this mess over time, we have to make a fundamental shift in our thinking. We have to leave the time domain behind and jump into the frequency domain. That's the only way to make sense of all this chaos. Okay, that totally makes sense. So if we're jumping into the frequency domain, I'm guessing there's a whole new language we need to learn. I hear senior engineers tossing around terms like PSD and RMS all the time. What are they actually talking about? Yep, and let's start with the big one. Power spectral density, or PSD. Honestly, the best way to wrap your head around it is to think of it as the recipe for your random vibration. Or another good one, it's like the graphic equalizer on your stereo. It takes that messy, chaotic signal and it just sorts it all out. It tells you exactly how much vibration energy or power you have at every single frequency. And here's what that recipe actually looks like when you plot it out. This is your classic PSD plot. Along the bottom, on the x-axis, you've got frequency in hertz. And going up the side, the y-axis, that's your vibration intensity, usually in units of g² per hertz. So it's pretty simple. The higher the line goes, the more vibration energy is packed into that specific frequency. And this plot, this is the key input for your entire analysis. Okay, so if the PSD is the recipe, then the root mean square, or RMS, is kind of like the summary of the whole meal. All it is really is the square root of the total area under that PSD curve. But what it represents is the key thing. Statistically, it's the overall average vibration level. And this is so important to remember. RMS is your 1 sigma value. It's one standard deviation of the response. Got it. So RMS is the average, the 1 sigma value. But that brings up a big question for me. Why do I always hear engineers talking about 3 sigma stress? If RMS is the average, why don't we just use that for our checks? Because designing for the average is a surefire way to have things break in the real world. Real vibration has peaks, sometimes really big ones, and we have to design for those peaks, not just the average. That's where the 3 sigma rule is our best friend. Your 1 sigma RMS value only covers about 68% of what's going on. But look at this chart. When we multiply that by 3, we get the 3 sigma value, and that covers 99.7% of everything that could possibly happen. We're designing for a near worst-case scenario, which is exactly what we need to do to be safe. So this brings us to what is maybe the single most important rule of this entire talk. If you take away only one thing, let it be this. You never, ever compare the RMS stress you get out of a Bacchus directly to your material's yield strength. You always take that RMS stress, multiply it by 3, and then you compare that 3 sigma value to your material limits. This is the absolute cornerstone of doing a proper random vibration analysis. Okay, this is really starting to click now. So where do we actually use this? I mean, what are some real-world examples where this kind of analysis is absolutely mission critical? Oh, it's everywhere. Absolutely everywhere. You've got aerospace and defense, where every little component has to survive the insane vibration of a rocket launch or a jet flight. That's all defined by standards like Millstand 810. Then you have the entire automotive industry, trying to simulate a car driving on terrible roads for 10 years. Think about your phone. It has to survive being shipped in the back of a rattling truck. Basically, it boils down to this. if the environment your product lives in isn't a clean, perfect sine wave, you're going to need random vibration analysis. All right, now for the part that honestly feels a bit like magic to me. How on earth does the software figure out the response to all this chaos? I mean, without doing a huge transient analysis that steps through time. That sounds like it would take weeks to run on my computer. It's not magic, but it is really, really clever physics. The technique is called modal superposition, and the intuition behind it is pretty cool. So first, the solver figures out all of your structure's natural frequencies. The best way to picture this is to think of your part as having a bunch of invisible guitar strings, each one tuned to a specific note. Then, that PSD input we talked about, that's like a rain of tiny sine waves that just pours down on all those strings at the same time, trying to make them all vibrate. And building right on that guitar string idea, imagine if that rain of energy from your PSD is coming down hardest right at the frequency of one of your guitar strings. If that string doesn't have much damping to slow it down, what's going to happen? It's going to start vibrating like crazy. And that, my friend, is resonance. The beauty of this analysis is that it instantly spots where your input energy lines up perfectly with your structure's natural weak spots to cause a huge, potentially damaging response. Those analogies are awesome. That really helps. Okay, so I think I've got a handle on the physics now. Let's get down to brass tacks. How do we actually do this? What's the step-by-step workflow inside Abacus? You'll love this part because it's actually really simple and elegant. It's a two-step process. That's it. Step 1 is a frequency analysis. This is where you find all those guitar strings we talked about. You're just figuring out the natural frequencies and mode shapes of your part. Then, step 2 is the random response analysis. This is where you apply the rain, your PSD input, and the solver calculates that final statistical RMS result for you. And just to give you a quick peek under the hood at the solver level, these are the keywords that make it all happen. You've got star frequency, that's your mandatory first step. Star random response is the main procedure. Star PSD definition is how you tell Abacus about your input recipe. Star base motion is what you'll use to simulate a shaker table. And this last one is so important, star modal damping. This is what controls how crazy the response gets at resonance. If you forget this, your results will just go to infinity, which isn't very useful. That's a super clear process, thank you. So let's say I've run the job, it's finished. What am I looking for in the results? And maybe even more important, what are the big gotchas? What are the common traps that junior engineers always seem to fall into? Okay, listen up, because this is it. The single biggest mistake I see time and time again is people misinterpreting the results. When you open up that results file in Abacus and you get that beautiful, colorful stress plot, you have to remember what you're looking at. That is the RMS 1 sigma stress. It is a statistical average. It is not the peak stress that your part is actually seeing. So let's just list out the top 4 pitfalls right here. Number 1, unit mismatch. Your PSD is in Gs, but your model is in millimeters per second squared. Your results are going to be garbage. Number 2, missing modes. You didn't extract frequencies high enough, so you missed a critical guitar string. Bad news. Number 3, getting the damping wrong. Just picking a random number, or worse, using 0, it's a critical input. And number 4, the one we keep coming back to, forgetting that 3 sigma rule and comparing RMS stress directly to yield. And here's how you turn those don'ts into do's. This is basically your senior engineer's pre-flight checklist before you trust any results. First, do a unit audit. Make sure everything is consistent. Second, check your modal mass. You want to see that cumulative mass participation is up over 80, maybe even 90% in the direction you care about. That proves you found enough modes. Third, review your damping. Use a value that makes sense for your materials. 2 to 5% is a good starting point for metals. And for the last time, I promise, scale your RMS results to 3 sigma before you do any comparison to yield strength. And that's really the whole story. At its heart, it's a statistical analysis. It happens in the frequency domain, and you're using a PSD to see how the natural modes of your structure respond. And the big takeaway is to always interpret those RMS results with the 3 sigma rule. If you can remember that and follow these steps, you are absolutely ready to go run your first random vibration job in Abacus. So we'll leave you with a final thought to chew on. Just look around you right now. What's a product you use every single day? Could be your phone, your car, your coffee maker, that was probably designed using exactly this kind of analysis. Once you start looking, you'll see the answers are literally everywhere. Thanks so much for tuning in.